from the NS franchise. He's worked on Gilenya. He's worked with award-winning teams on Gilenya. I think he got a development award in 2013. And his real passion is graphics. So I hope today we can share his passion. And I've seen his presentation, and I think you'll all enjoy it. Okay? Thank you very much.
Thank you very much, Joseph.
You got your...
And that's how I switch the slides, is it?
That's the pointer pad?
That's the pointer pad.
Yeah.
I just switch slides.
Ah, there.
Okay. Yeah, fine. Thank you. All right. Okay. So I'm well equipped. Good morning, and thanks for the opportunity to talk here. I will talk a little bit about graphics, obviously in the application and in the pharmaceutical industry. Graphs that I've really used. We'll see them, and I will also talk a little bit about some technical, basic implementations and things that I think are important when graphing. I want to start with this citation from Hans Rosling. He's the founder of Gapminder. Hands up, who knows the website, the Gapminder website? Not so many. Go to the Gapminder website and check it out. OECD, and I think that goes a bit in the direction of the first presentation we've seen, where you can rearrange data and so on, and analyze the data yourself, and look at the health, for example, over time, how it developed in different countries and so on. It's very interesting. And anyway, he compares statistical data to music, and he says most people are not able to appreciate the notes if we just show the notes, and that's often how we present a table or statistical data. Instead, we should play the music, and then they're more able to understand. Everyone is more, it's easier to understand than the data. So we should not just show the notes, we should play the music. Now, before I go into that, I would like to show two things that I personally find very important when I do my own graphics. They're often packages. They do the graphs relatively quick and in an automated fashion. I think that's very good for when you want to explore the data, understand them quickly. Once you have an understanding of the data and you want to present the information exactly as you have in mind, then it's important that you can control where different plotting elements are in your graph, that you know which element is on top of which other element, and if it's more complex information, that you can arrange several graphs on one page in the way you want. That's this plotting matrix topic I have here. And most importantly, think what you're plotting. I think we've seen that in several presentations. Think what you want to display. It depends on the audience. It also depends on the content that you want to, the purpose of the exploration of what you want to show to the audience. It may also depend on the audience. So depending on all these things, you may have a different plot for the same data set. In a second part, I will show some real-world pharma examples. For example, a change from baseline. Also a graph that I used in the planning of a study, an overview of safety, and I have also some exploratory plots here that we used in the context of health story questions. The examples are all real. I've used these plots, but I've always modified the data, so you don't see the actual data as it was, so just so you understand. So for the technical aspect, I think usually we want to predict something, like we have an exploratory variable on the x-axis and something on the y-axis. We may want to add colors, and that's what I understand when I talk about the layer plot, where you can add different plotting elements on top of each other. For example, a line from a model that is on top of these dots, or maybe a confidence interval, and now that confidence interval is underneath the plot, the different dots, and underneath the line. And maybe we want to have prediction limits, and again, they are now under the confidence intervals, the dots are on top, and the model fit is on top of that. So we want to have good control of which plotting element comes in which order. And I just show a small piece of our code here, and I think you could do it in another environment as well. Basically, we open a kind of a plotting region, and then we have this polygon here, which is this confidence interval, and then we add the points, and then we add the lines, and if by the order of the code, it controls the order in which the elements are on top of each other. So I think that's one of the important elements that I use a lot in order to control graphs. And the second one is this plotting matrix, so that you have control over how you want to present several plots on one page. So there is a first graph and the second one, a third and the fourth. So I show you how that is done. So this plot is actually formatted as a plot. So there's this first plot, and then the number is put inside this plot, and there is a second and a third and a fourth plot. So then I populate these. That's how it was done. And when you look at the R code here, then you have kind of a matrix 2 by 2, and it's populated by row. And in this matrix, I submit the orders. So the first one is the second element, so the first, the second, and then you see the fourth goes in this because it's populated by row. So this comes as third element, and then the fourth element is number 3. And then we have 1 plot, 2 plot, and I can actually arrange them in a different way, and I can arrange them, populate them with different graphical elements. And now we've seen for each plot, we've seen how we can stack different elements on top of each other, and we've seen how we can arrange different plots on one page. And with that, we have pretty much full flexibility of what we want to present. So with that, I stop with the technical aspects and want to move to actual examples. Andreas before already showed change from baseline over time. That's something we often want to illustrate, and often we want to explore the data. And quite often in tables we look at mean values, often ranges are plotted, but in my experience no one really looks at these ranges. But often it would be a good idea to also identify whether there are some issues with the data, maybe it should be raised to data management. So here I actually use such a plotting matrix, and you can see it has here 4 columns. So for each dose, 1, and as by the recommendation of Andreas, we have this symmetric to the no change line here, which I put into the graph. And on the x-axis, you see the different visits: baseline, month 6, month 12, month 24, and then we plot the actual data for the different treatments, and you can now see certain elements. For example, we can be interested in who has a maximum increase, and are increases sustainable over time, or do patients go back? For example, this patient went down but then came up again. We can also see in placebo we have a lot of values down here, not so much in these. There's this extreme case, maybe something that should be cleared by data management, and we can see the individual plots here. Data points. It's obvious that the same data, if you were interested in a treatment effect, that's not a good plot. We can't really, it's difficult to see whether there is statistical significance in terms of a treatment effect. But we can judge on say, variability at certain points in time and compare it between treatments, or we can see that there are a lot of values down here and not so many in this plot, and so on. So my second example is from the planning of the study. A while ago, in 2012, we were in the position that we started the study, and Health Authority said they need the report of this study 3 years later, in November 2015, so it would be next year. But we were at the very beginning of this trial, and we just started to recruit patients, and recruitment was really slow. So the clinical team was worried that we would miss the time to submit this final report, and we were discussing what could be done. And especially the discussion was about whether we should reduce the study duration in order to make it to the database lock date, or whether there should be an interim analysis, for example, and what the properties of this would be. And there was a lot of back and forth. How many patients will we have with 1 year or 2 years of exposure at a certain date and time? In March 2015, it was for the database lock that we would need to have. And so I asked them for their projections of by when we would have these centers open, and then for each patient, so the plan was to have 200. 200 patients in total here, indicated by this blue line. You see the number of randomized patients on the y-axis, and you see the calendar time in dates on the x-axis. And I plotted from these projections of when they will open their different sites. For each patient, I plotted a line. So you see in dark gray when the patient will have 1 year of exposure, and in light gray when the second year of exposure will be finalized. And the health authority report needs to be submitted November 2015. So you see this as this red arrow, CSR for the interim analysis, and here the database lock in order to make that also in red. And you can now see that if we really make it in this expected fast scenario where we increase, where we triple recruitment, we can just make it or just not make it to have everyone completed at the time of database lock. So even in this relatively optimistic scenario, it is just tight, but it's probably possible. So maybe you don't need an interim analysis. Here there's some text that's just to show what the statistical properties at the interim analysis would be if we had this interim analysis. And then you can use the same program. It's basically, in SAS you would say a macro function, where you can replace certain parameters, and then you can see when recruitment is slower, then at the time of the interim analysis, we would actually not have this piece of the data. So only about 85% of the patients, you see here, there's a proportion of randomized patients, would have completed 1 year of exposure, and only about 25 would have completed 2 years of exposure. So you can see this, and I think it's intuitively clear what it means. You can also see the final report of the first of last patient, last treatment, and the final CSR in blue. And now we can still make it with this interim analysis if we have this interim analysis, and also the properties. I'm not going into that of the interim analysis. They were relatively good. We didn't have anything to lose, so we decided to have an interim analysis in this plot. And you can see how things are plotted in gray, most of the things here, but you also see that the really critical timelines here, they're put in red in order to highlight them. Then a quick overview of safety, completely different topic, also in setting of clinical trials, where you have data from one trial or possibly several. So the question was, can we provide a graph where we can have an overview of safety, for example, by SOC levels, maybe with preferred terms inside, or by risks and preferred terms. And we would like to read off the frequencies of these adverse events by treatment. We'd also like to have an understanding of the imbalances versus the control treatment, and the different doses of active treatments. We would like to have an understanding of the seriousness of adverse events, so it could also be the severity. And if possible, we would like to squeeze that all on one page so that you have an overview. That will not replace a detailed review of the safety database, but is it possible to combine this information? How could we plot safety information? So a first suggestion maybe is something like this. Now you see in the legend there is a high dose, a low dose, and placebo here. And in terms of colors, I keep the control always kind of neutral, either blue if I use colors, or gray. And high dose to low dose, if you have more than two, I always use kind of, it's called fire colors. I think that's pretty intuitive. So the highest dose is red, and then it goes to more yellowish colors as you go to lower doses. So here there are only two, but you see the high dose and the low dose. And you can see now I use this bar because everything is compared to control treatment. So for the control, I use the bar, and you see when the dot is on top of the bar, then on active it's lower than on comparator. If the dot is in the white space, then it's basically a safety signal. Now you can also see that I ordered everything by the frequency on the highest dose. And I don't think that's very good, but that's often what we do in tables. It usually highlights things that are common, nasopharyngitis or something. Okay, but what you don't see in a plot like this is, it's doing very, very poorly here. The cortex symbol, I think it's this one, yeah, battery is flat here, where you see some events in this SOC on active treatment, but you have none on the control treatment, and it's easily missed on this plot because you highlight the most frequent things. So now we have a plotting matrix 2 by 2. There's one plot where you see the frequency, and it's now ordered by the imbalance here, in this case an odds ratio. And I come back to the question that we had earlier. So it's here an odds ratio, and you see on the x-axis of this plot, the numbers are still there in an intuitive fashion. So you see 1, 2, 3, 4, 16. It's not a log scale on the axis, but the values that are actually presented on a log scale, so the confidence interval is symmetric. You also see elements that go outside the plotting region. For example, confidence intervals, they are shown as an arrow because they extend to outside the plotting regions. And you also see at the top, like the cardiac signal, for example, the estimate is far to the right. It goes to infinity because you only have cases on active treatment, but none on control. So it tends to go to infinity, and I indicated that by this arrow that goes outside the plotting region. And possibly now we can add a third panel here to also indicate the seriousness, and you can see now in the third panel the frequency of serious events within this plot. And it's also possible, of course, to have that now by SOC and PT within SOC. But now, as I use about 750 patients or so, I have to have a certain selection criterion to select the ones that I want to see, and obviously it will depend on what I select. But in my program, I can now change the selection criteria that you have in the footnote, and then look at different views of the same plot. And that helps me a lot to understand the safety profile quickly. Now, as a last example, I would like to show you some interaction and outlier plotting. There was a health theory question, and that's about our efficacy data. So they said you have a significant treatment effect, but also a significant treatment covariate interaction, and they did their own analysis, and they said you also have some kind of outliers, so you should identify them. They didn't define them for us. They kind of hinted what do they mean by outliers, but they didn't really define them. And then we should describe the influence of outliers on our results. So when you look at the statistical table from this model, it's about recurring events. So people have certain events, and we observe them for a certain period of time. So we look at a negative binomial model, and then analyze it. We get this deviance table, and you see here the type 3 treatment effect, which is significant. And you can also see that the treatment effect is the treatment times covariate effect is also significant. So it somehow means that the treatment effect, depending on whether you're on the left side of your covariate or to the right side, is stronger on one side than the other. It may even be inverse that you can't judge from this table. So by outliers, no, I should show this first. So what they've done is they looked at, for each individual patient, how many events did the patient have, and divided that by the time the patient was in the study. And what you can see now, or what you know from just common knowledge, is that patients usually within a year have 1 or 2 0 events. It's very unusual for someone to have 4 events within a year, and it's almost impossible to have 11 or 12 events. And you see these dots up here where you have actually high values. For most patients, you can also see they're kind of aligned at the bottom in these rows, and that's because it was a 2-year study. So if they had 1 or 2 events, you see all of them kind of aligned in a row. But there aren't these top values here, and the question was, what's their influence on the analysis? So we had a discussion about what the outliers mean, and one is it means everyone who has more than 2.5 events per unit of time. That's one possible definition. Another one would be patients who have spent a small period of time. They had, for example, an event and then dropped out early. We would, by dividing the individual number of events by the individual time spent, we would kind of inflate that and artificially have these outliers. So we can remove the ones that spent a short period of time, and it would delete the observations that are crossed out in green here. Crossed out in green, maybe it should be crossed out in red. But on the other hand, you had placebo in red, so maybe you can swap the colors. So the plot we provided was this. So on top you'll see the individual patient data for placebo and for active, and then you see the model fit here. For placebo, so on average 0.8 events per unit of time on this side of the covariate, and on the other side of the covariate 0.4. And on active treatment, it's always low at about 0.2. And in the third plot down here, we see the relative treatment effect, so it's active to comparator, and I can't show it. On the left-hand side, the relative efficacy is about 80%, and on the right-hand side, it's maybe about 30%. But you can also see it's always to the good side of placebo. So we always have a beneficial treatment effect, even though it's significantly different on one side of the covariate than on the other one. That's the main result. And then next to it, we've shown what would happen if we delete this first definition of outliers, and the model fit how it would change and how the efficacy would change here, and how it would change when we use the second definition of outliers. And you can see the model fit does hardly change at all, and also the relative efficacy doesn't change. So overall, we can conclude that we have a benefit across the entire range of the covariate, and that these outliers that health storage asked us about, they're not influential on the analysis. So with this, I'd like to thank you for the opportunity, and prepared to take questions. Thank you.